Wonderful. It's been a total joy to be here, so thank you so much for the invitation. And make it a little higher. Okay. Okay, great. Hopefully you can hear me. And I've had many wonderful conversations, both with members of the MVAPage team and other people in the audience. And I've actually learned a lot, and you'll realize that the tutorial that happened on Monday is very apropos for some things that we're trying to do at Stony Brook. So I'm going to give some perspectives on not just MPI, but high performance computing in general. So much of my career has been motivated by advancing my own original discipline of theoretical and computational chemistry, meaning the using quantum theory to compute the electronic structure of molecules and predict all sorts of things that chemists and material scientists and others are interested in, both for basic research and also more engineering applications these days. But of course that gets me into the intersection between this science domain, applied math, and computer science and computational science fairly broadly construed in order to handle these complexities. And sort of it's really from that perspective that all of the perspectives I'll be sort of looking at sort of all start from that higher level perspective of managing the complexity and performance issues in modern HPC. So I've got a bunch of topics that we'll be covering. I'm going to start off talking about this new testbed system we're in the process of deploying at Stony Brook. Talk about a science application that sort of, it's now nearly 20 years old, somewhat shockingly, but it's sort of motivating large chunks of what we're going to talk about in the rest of it. Talk about some issues it revealed and were resolved by the OpenMPI team. And again, in collaboration with some of the OpenMPI team in developing a new, essentially data parallel programming model, data flow programming model. And then I'll talk about, at the end, about sort of this larger activity, Molecular Science Software Institute, that is essentially a community scale activity within the entire molecular sciences community. Okay, so Okami. So Okami is the Japanese word for wolf, which pays homage to both the Japanese origins of the technology that we're going to be talking about, as well as the sea wolf logo at Stony Brook. This is was just funded. It's a $5 million project from NSF. About half of that goes to hardware, half of it goes to operations over a 4-year period. The configuration is on the far right-hand side. And so the key thing is, as was discussed actually right at the beginning of this workshop by the representative from ARM, it's deploying the first generation of modern ARM processors for HPC that incorporate the scalable vector extensions. And most excitingly, also incorporates an extremely high memory bandwidth. So there are 2 or 3 different ways of thinking about this. Maybe that first way is sort of like it's ARM moving forward to be relevant to HPC. Another aspect is you can think of it as a very programmable many-core processor, multi-core processor that gives you high memory bandwidth. But another perspective, and from that perspective, it could be sort of viewed as like KNL or KNC done right, fixing many of the warts that were in that architecture. But another perspective is actually it's sort of like a GPU in terms of the performance it can deliver, but with the many of the programmability characteristics of a CPU. So it has each processor's got 48 cores with 4 helper cores on it. We're going to look at the architecture in some more detail. Its peak double precision speed per processor is 2 3/4 teraflops, but it has good support for a wide variety of data types, and its highest performance operation, which is essentially accumulating, doing multiply add operations of integers accumulating into 32-bit floats, is running essentially 8 times that speed. The memory is somewhat modest, and we'll go into details on that, but the key thing is that very high bandwidth, right? And you can actually get at that bandwidth. We'll see that in a moment. It's just a test bed, so there's not a huge number of nodes, and there's a sort of fairly modest parallel file system on it. We intend to deploy not just this generation, but the next generation of this technology. It's a key thing to realize that both in Japan's pursuit of ARM technology for exascale, but also Europe's, that it's a technology path that you're buying into. It's not just a one-off system that we're exploring here. Key to making this happen has been a strong partnership with the team in Kobe in the Riken Center for Computational Science. So I'm going to go into all of this in somewhat more detail. A key point here is this increasing dominance of accelerators, primarily GPUs in modern HPC, especially at the high end. So this is a description of Summit, the currently fastest computer at Oak Ridge National Lab. And essentially 90% of the flops come from the GPUs, right? That's in double precision. If you look at reduced precision, then you're going to be looking at 96+% of the flops coming from the GPUs. So amazing performance, but clearly challenges for a lot of applications in programmability. Certainly in my own domain, chemistry, material science, I would say less than 30% of our science capability can exploit GPUs effectively presently. And that's a major source of frustration. And of course, we all know that the next generations of machines are going to be all GPU-based in performance, right? Despite the best intentions of, say, people at Argonne to deliver CPU-based HPC systems, everything's GPU. Of course, the US is no longer the only game in town when it comes to HPC. Other regions of the world are investing extremely heavily and aggressively in this technology that's important to many aspects of science, society, and other strategic concerns. But the path that we're on in the US, right, isn't the only path that's available to us, right? And this technology path that's based on ARM and scalable vector extensions is pursued. Here are some links to both the European project and the Japanese project. And the key thing about the ARM ecosystem is it's massive, right? x86 is tiny in comparison, right? 20 billion units a year versus just a few 100 million for x86. Now, of course, most of these are tiny things in mobile settings, embedded settings, and so on. But what it does mean is there is a rich, mature ecosystem out there. On our advisory board is Simon McIntosh-Smith from Bristol that's fielded Thunder X2-based system. And he's very successfully demonstrated the robustness and maturity of the scientific stack for HPC, and that modern ARM technologies, with some caveats, are able to deliver compelling high performance on a wide variety of scientific applications. And A64FX is essentially fixing many of those caveats in terms of the performance delivered. And again, it's a technology path. We're in the process of taking this processor. This is the processor that's going to be deployed in Fugaku, the Japanese post-case system. But next generation systems are already in the pipe. And this presentation here from Sato is actually a great one to look at to get all sorts of gory detail on the processor. So here's the processor at a glance. Looking at a single core, there's 52 cores on the chip, 48 for compute, 4 associated with running the OS. They're identical cores, there's no distinction between them. 64-bit, 57 gigaflops plus per core, and you basically, as you get more elements per vector, the performance increases accordingly. And here are some key stats, right? One key stat is if we look at the stream benchmark, you can achieve an extremely high fraction of that peak bandwidth, right? And you can also achieve an extremely high fraction of the peak double precision speed, right? It's an extremely programmable device in the same sense that it's easy on a GPU to access the memory bandwidth. The same thing will be true on this platform. And there's some comparison to more mainstream technologies. Looking at the architecture itself, it's a NUMA architecture, so again, the analogy to KNL actually holds fairly true. The chip's divided into 4 regions that Fujitsu is calling a core memory group. Each one's got 12 compute cores plus 1 helper core. And there's essentially a crossbar in the middle. Speeds and feeds are on this next slide. So this zooms into a core memory group. Looking at a single core, it's able to run a DAXB at full speed out of L1. And there's the bandwidths right here. So if we look at this bandwidth here, then you can see that the read bandwidth corresponds to reading a single vector at full speed, and you can do that all the way down into main memory. So a single thread can achieve a very high fraction of its necessary bandwidth running out of main memory, right? And so that really will change the performance profile of applications. If you look at, say, a program running on x86, the realizable bandwidth from a single thread is perhaps 12 gigabytes a second or something like that, right? Even though the total system might have a memory bandwidth of, say, 100 or 200 gigabytes a second. Here we've got a total aggregate system bandwidth of a terabyte a second, and a single thread can get a very large, can get 10% of that. Then there's essentially a ring, so that's crossbar that's connecting everything together. Of course, on this first generation system, we're limited by available high bandwidth memory technologies, and that includes the capacity. So you have to ask, what is the relevance of this, some would say, small memory for real science applications? One of our partners on the project, Matt Jones from Buffalo, is a member of the XDMod project. And they've got all sorts of stats on the entire NSF Exceed workflow. These come from, if you just go to archive and search for Exceed workload, you'll probably find this paper. And you can basically see here that 86% of the jobs on all Exceed systems in 2018 that correspond to 85% of the cycle. So there's an interesting one-to-one correspondence there between jobs and cycles used that's independent of the size of the job. Can fit, including the OS and file buffers and everything, into 32 gig. Now, of course, that's squeezing in. You might need a little space in order to get robustness and everything. But this is an extremely indicative statistic when thinking about how much of Exceed's workflow can fit not just onto this machine, but what the Exceed hardware ecosystem should actually look like. It's not cost efficient, it's not power efficient to be configuring every single machine to run the worst case of all possible jobs. Right? Clearly, some science, some jobs need a very large amount of memory, both for performance reasons and ease of programming and all of that jazz. I certainly have many jobs that need more memory than this in my own portfolio, but nevertheless, a very large fraction of what people do will easily fit on the proposed system. And clearly, future systems are going to have more memory on them. This is some stats not about capacity, but about memory bandwidth, indicating that a very large fraction of Exceed jobs are actually consuming a large fraction of available memory bandwidth. Now, that's not to say that they're limited in performance by that memory bandwidth. We're talking with the XDMod team about how do we capture statistics to make that additional level of conclusion possible. But it isn't indicative that many applications are poised to benefit significantly from the key feature of this machine, which is the extreme memory bandwidth. There's a bunch of people involved in the project. I've already mentioned Matt Jones. Alan Calder's in astrophysics from Stony Brook, and he's going to be leading our scientific community engagement team. Barbara Chapman is probably familiar to everyone in this room, the lead figure in the international OpenMP community. She's going to be leading up the research and development group. We're actively funding a graduate student to bridge between her team and scientific applications, basically to bring best practices to the application teams and then to bring unmet needs back to Barbara's group that essentially will establish new research activities. And Barbara's already got a long-standing collaboration, both with Matt Soroka's team in Kobe and also the Fujitsu compiler team. Machine's going to get deployed sometime early fall in this coming year. That's roughly 6 months after the initial deployment of the machine in Japan. Don't need to go any of those. The slides are presumably going to be available, so you can look at the additional detail. So now I'm going to talk about MADNESS, which is a project I've been working on with many other collaborators around the world for some years now. It's essentially a general purpose numerical programming environment. It was motivated by problems in chemistry where we've got challenges that mean in our mainstream ways of representing molecular wave functions, we've got challenges in efficient computation, meaning the computation scales non-physically as a high-order polynomial power the size of the system. And as we seek more accuracy, not only does the cost of the calculation increase, we also get numerical stability problems due to essentially over-completeness in the basis set. So those were the initial two motivations, but we also wanted to do something about this semantic gap. So many chemistry codes are massive. We'll see more detail about that towards the end of the talk. But our equations are relatively concise, right? We can get our equations on a few pages of algebra, but our codes are literally a few million lines long. So this disconnect is really disconcerting. And so we also, of course, want to have our code portable, performance portable from the machines we develop on to the machines that we run on. So MADNESS is trying to address all of this stuff. It does some well, it does other things maybe not so well. At very highest level composition environment kind of looks like this. If there's any chemist in the audience, this is solving the E-Hartree-Fock equations for the helium atom. But for everyone else, it doesn't really matter. What's crucial here is that the composition is in terms of functions and operators. It's not in terms of coefficients or sparse grids or matrix elements. And instead of computing with the derivative operators, we try to rewrite our equations in terms of the integral operators. And that has significant benefits when it comes to the numerics of the calculation and also actually to some aspects of the efficiency of the calculation. This pseudocode, it's not just pseudocode, it's real. We can compile this into parallel C++, but in the end, this high-level DSL isn't very robust or complete, and so it's useful for situations like this, introducing people to how to think about how to write a MADNESS application at a very high level, but at the lower level, people are in practice writing C++. But the C++ is essentially has a one-to-one correspondence with what you can see here. Behind the scenes, this just an adaptive mesh, right? This is a 3D picture of actually two benzene molecules side on, and this is a molecular orbital spanning them. And it's the usual adaptive mesh where there's stuff going on, there's some refinement, and where there's things that are not changing rapidly, there's large boxes. Inside each box, we have a basis set that's presently chosen as a tensor product of Legendre polynomials. Legendre polynomials are easy, familiar, orthonormal basis, and so pretty much most computational scientists can get familiar with the basis set quite rapidly. Layered on top of that basis set are some things that give us fast, accurate computation. The two main concepts of this idea of multi-resolution analysis. So imagine we have a sequence of, let's say, grids of increasing resolution. So V0 will be your coarsest grid, V1 the next finest grid, and then going all the way down to the very finest grid, Vn. Instead of thinking about the representation of our solution at each scale of accuracy, we think about the representation on our finest grid in terms of the representation on the coarsest grid plus corrections at successive length scales. So the multi-resolution representation is looking at the differences. And you should be able to see that in a place where the function is behaving smoothly, changing smoothly, maybe we can represent the grid accurately at level 1, which means that successive differences are negligible. Whereas if the function is wiggling, we have to resolve down to maybe the finest level. So what you can see we've done is translate smoothness into sparsity. So that's one key technique here. And we can do this in a way that mathematically rigorously controls the accuracy of computation. And so that's a key thing in that we can essentially maintain accuracy regardless of the physics. And the computation is designed to just scale linearly at each step with the number of coefficients that are present. Okay. So that we have some guarantees on speed and accuracy. Okay. Obviously, a guarantee of accuracy may come with a speed that you find unsatisfactory, but ultimately, some things are worth paying for. The other key thing is making this work in many dimensions, and so there's a lot of work in taking multidimensional kernels of operators and generating very accurate and efficient separated representations to essentially sidestep the exponential curse of dimensionality when it comes to applying integral operators. And I'm not going to talk about that today. But basically, all of this together means that we have a very dynamic computation. And the key thing is nothing is done accurately. We do everything to the precision requested by the user. So it's not that we look at some numbers and say it's small, I'm not going to compute it, or say, oh, that number's big, I'm going to compute that number. Even for the big number, we only compute it to the necessary number of digits, right? And so we trade precision for speed everywhere we can. And I like to think of applied math as the rope that enables us to sort of like climb down the cliff in a safe way. But what this also means is that everything is extremely dynamic. And that sort of launches us off into what will be sort of like the middle of the talk, talking about the parallel computing section. So what we want to do is express all of the available parallelism that's going on in this computation. And so we do that sitting on top of a parallel programming runtime that sort of dates back probably nearly to 2000, but really didn't start coming into substance until we got, I think it was the Cray XT3 at Oak Ridge, so about 2004-05. So the MADNESS architecture is pretty standard. We got the physics applications that you've sort of seen in that very high-level depiction that sits on top of the multi-resolution math layer that is sitting on top of the parallel runtime that I'm going to talk about, that obviously is heavily using MPI and is using a bunch of other things for some aspects of computation. So I'm going to skip over that. Already mentioned that why was this new runtime instantiated? Basically, because we were trying to support this very dynamic computation where every single operation on a function would essentially lead to a new grid. So we don't have a single grid on which all quantities are tabulated at every grid point. We actually have, for each function we're interested in, we have a separate grid. Clearly, if everything is at the same level of refinement, that would be inefficient, but in the types of computation we're doing, it's not. So you can imagine a very large molecule. Some functions are localized over here, some functions are localized over here, some functions are localized at a very fine scale around the center of an atom. And so for our computations, there's significant advantage in having separate numerical representations. But this leads to a much more dynamic programming environment where we've got complicated data structures that are constantly changing, distributed across the whole machine. We did explore a bunch of other technologies, and for reasons that I won't go into right now, none of them really work. We actually had a complete implementation on top of MPI, but it was extremely cumbersome because with MPI as the explicit level. So going quickly through the components of the MADNESS runtime and programming layer. At the very lowest level, we build on top of essentially two things. One-sided active messages, or essentially RPC, and a pool of tasks on each processor, inside each process. So our model is message passing between multi-threaded processes at the lowest level. Then we build on top of that, and we add features to hide latency. So whether that's algorithmic latency or latency for message passing or I/O or some other external activity, those are composable. We'll see that they can be used as an input for tasks, and that enables us to build essentially a DAG at runtime. We have constructs that give us names that make sense across the entire machine, and then spaces in which we can store object using names that make sense to the application. And we try to relieve the programmer of the burden of worrying about placement and scheduling of data and computation. I say try because we're not completely successful in doing that. And of course, we need some dynamic load balancing. We have several approaches to this. Randomization is easy but not necessarily efficient. We have various heuristics for data redistribution that we can do sort of semi-dynamically. We had a work stealing implementation, but the implementation was never very robust. The person went off to work, I think, for Intel, and eventually we ended up deleting it. Futures are probably familiar to most people in the audience, but we have inside MADNESS futures that understand the distributed computation. So we can initiate a task on some remote process, have the result of that assigned into this result, eventually assigned into this thing that's wrapped in a future. And we can, before this computation is complete, use that in a subsequent computation on another processor if you wanted to, and essentially here now build up this dagger computation at runtime. And the key point here is we want to express enough computation and data motion so that we can be successfully overlapping computation and data motion to essentially hide as much as possible all of the latency associated with the communication. And again, algorithmic latency associated with dependencies. We build objects that essentially have the same name in a given application. So for instance, here this instance of this class would exist in all processes, and you could launch computation in each instance of those, invoking methods of that object. And that's all done just building straightforwardly on top of the active message layer. But that scaffolding then makes it very easy to construct more complicated distributed data structures. And I'm not going to go through that, but it essentially enables us to have computation that's composed as message passing between these objects and containers. And essentially that's a key idea of both Python and Charm++, so on. There's a couple of examples. They'll be in the slides that people can go through if they're interested. Underneath all of this, we sort of have a fairly straightforward model in the MPI implementation. There's a server thread that's processing incoming active messages. There used to be a portals implementation on some old Cray system, but that's now defunct. There was a PAMI implementation on top of BlueJean, but that is also now defunct. And so really the main implementation right now is on top of MPI. The PaRSEC team at the University of Tennessee, they have some of the MADNESS runtime now built on top of PaRSEC, but that doesn't yet include the active message layer. We're in the process actually of trying to recode the entire lower level of MADNESS. And we'll see a little bit about that. So it's essentially a multi-threaded process with a communication thread, a bunch of threads executing tasks, and then a single thread that logically is driving all the entire computation. Every single one of these threads can and will aggressively send messages, and that's been one of our major challenges interacting with MPI, is extreme multi-threading. We've got lots of issues associated with the code. The style of composition lends itself to users specifying way too much parallelism, and there's various mechanisms we have for trying to throttle that, but in the end, none of them are really powerful enough, and especially when it comes to managing memory and communication, something's got to get done about that. In terms of performance, a key problem is actually when we're running on top of an InfiniBand system, MPI wants the memory to be pinned and replaces the malloc with its own, which is infuriating because the MPI malloc is typically slow, right? If you look at a state-of-the-art malloc like TC malloc or JE malloc, TBB malloc, they're typically potentially 3 to 5 times faster than either the system or the MPI malloc, especially in a multi-threaded setting. And so in a heavily object-oriented code, right, if we have a fast malloc, you can get away with mallocing lots of small objects, but doing smaller, clearly, if malloc is slow, then it becomes a bottleneck unnecessarily. So that gets me into, yeah?
Just a quick question. So one of the reasons why MPI libraries intercept malloc is to get better performance for larger messages. So to avoid and amortize the cost of registering the buffer with the equivalency. So if MADNESS does not have large messages, this can quite easily be circumvented.
Well, that would be a great tweak to put in there. I mean, I know that various users occasionally get back to us, always rediscovering that if they link in their own fast malloc, eventually there'll be some sort of either incorrect data will be sent. So I've certainly seen situations where you can see a send and the wrong data is received on the other end because I guess there's confusion about what was pinned, or things just segfy. And so I don't know if that answers the question that maybe there are some large messages.
Probably there are. So again, there's something that we can take offline.
Yep. So
this can be fixed. Thanks.
Be great. Okay, so OpenMPI, basically, because of the collaboration with the team at UTK, so all of this next few slides are from George Basilka and his team. Basically, well, George is a hardcore C programmer, so he looks at C++ in horror. I have a love-hate relationship with C++, I must admit. I mean, it's a very powerful language, but it's also horrifically complicated and large and changing very rapidly. It starts to look more like Python these days, which might be a good thing. but in connecting that modern C++ programming model with sort of the low-level C runtimes is somewhat challenging. And again, I mentioned some of these issues here that come up in performance. And so when we initially tried to get MADNESS running on top of OpenMPI, there were some major issues. Part of it was to do with the granularity at which stuff was threaded. There was an actual bug in the memory allocator that was exposed running in this heavily multi-threaded setting. And then there were some other issues associated with use of MPI 3.x. I must admit, I don't know what any of these words here mean. I think these are the times on these various platforms using in seconds to run the application, and this is Intel MPI down here. Basically, one of the key steps was to do finer grain locking around the multi-threaded communication. So I assume, even though this is OpenMPI, that you're familiar with what these guys are up to. And that enabled them to make some significant inroads on the performance, essentially going down essentially nearly a factor of 5 increase in performance there. Right, so I think that was that factor of 5 that we just saw in performance. There were some stats that actually, it was a bit frustrating. I asked George for some slides on this, and he sent all this amazing detail that I wish I'd had like 5 years ago when he got the data. And so this is sort of illustrating several nice things. That nearly all of the communication inside MADNESS, this is just a small calculation on a cluster of 5 water molecules. Essentially all of the communication is through asynchronous operations. In fact, I'm surprised to see any synchronous operations on there, so I don't know where that's coming from. And so they're apparently, and then we can also see that there's a whole load of messages that sort of like come out of sequence. And apparently they can use that data to essentially put their finger on some parameter associated with the eager message protocol that can actually handle, essentially reduce the runtime down to get most of that speed up that we just saw.
So just a quick comment. So if you remember the established tutorial, we had mentioned a couple of cases where the routable messages can get delayed if there's a load and balance problem or things like that. So this is exactly what is being done here. Good.
It'd be super cool to be able to just detect this at runtime and have the problem not appear in the first place.
Right. So in Dr. Parda's overview slides, basically I had a paper at IACS a couple of years ago which tries to do this dynamically. Unfortunately, we have not been able to bring it into the code, so that's one of our things on the to-do list.
Okay, cool, great. We'd be happy to help. Okay. These are some projections that, again, I don't completely understand, and it seems to be trying to set my expectations to be low in terms of multi-threaded message rate. So if I'm interpreting this correctly, is that using these various versions of MPI, that this was the message injection rate in a multi-threaded setting. This is just single process MPI. And then this seems to be the target still for a multi-threaded setting, which is still significantly less, right? We're on a log scale here, so this is like a factor of 20 or more difference. So I don't understand, I guess, what should our expectations be? What should our design principles be in designing a multi-threaded code that wants to do message passing? Is it basically simply a bad idea and we shouldn't be doing it? Or are there some design techniques that we should adopt?
I don't think it's a bad idea. It's just that the current generation MPI runtimes don't have support for fine-grained locking, as well as multi-endpoint based designs, which are a necessity to have kind of process-to-process practical peak to be obtained for multi-thread performance. The libraries are heading in that direction, but they are not there yet.
So I mentioned that we're looking at new generation of parallel runtime and also programming model for MADNESS. That's this TESSE environment that I'm going to talk about for a few minutes. So task-based environment for scientific simulation at extreme scale. Everyone needs a good acronym. Essentially, what this is doing is it's building on top of the work of the PaRSEC team. So PaRSEC is essentially it's a powerful runtime that can do all sorts of stuff, but what it primarily provides is DAG or dependency-based composition of mathematical algorithms and translates that into distributed computation that it then takes, meaning the runtime, then takes responsibility for motion of the data and scheduling of computation, including efficient use of GPUs. So once it understands what the lifetime of a piece of data is in a certain setting, it can actually move the data, keeping multiple copies of it appropriately, updating those copies, and then moving copies back once updates are complete and so on. So that enables use of the GPUs in addition to remote computation. The initial problem that this project was really addressing with PaRSEC was that this has historically been done only in the setting of static computation for dense linear algebra, whereas both of the driving applications for this project are looking at very sparse, very dynamic computation. MADNESS looking at very fine-grained, in a relative sense, computation in the multi-resolution tree-based computations, and then the other driving application, TiledArray, a many-body physics code, is essentially doing block-sparse tensor computations, where now these tensors might be 4D or 6D, and the blocks of each tensor might be somewhere between 10 and 100 in each of these dimensions. So much coarser-grained computation. So basically, a key goal was to extend this to handle a much more irregular composition, much more irregular applications, and develop on top of PaRSEC a programming interface to support those applications. There's actually a follow-on project to this. So this is this EPEXA project that was just funded by NSF under its CSSI program. And so it's essentially taking the programming model that we developed under TESSE, taking it from research prototype into a production quality ecosystem. So this is a 5-year project, and a key part of that is developing multiple interfaces to multiple backends. So mature the high-level programming environment, insert in the middle a portability layer, and provide underneath that multiple backend implementations. We already have implementations on top of the MADNESS runtime and on top of the PaRSEC runtime, and we want to extend that onto other runtimes. And it's very natural to me that one of these should actually be closely integrated with MPI. So the main project's objectives, I sort of roughly described them. We want to transform the programmability and scalability of the two main codes in the project. And in the larger CSSI project, there's actually going to be multiple codes from a larger developer and user community that we're developing. Pretty much gone through that. So the key concept here is this idea of that really comes from PaRSEC itself. PaRSEC has this PTG, parameterized task graph, where the parameterization here essentially in terms of template, because we're referring to the C++ uses of templates. But the key idea is to parameterize tasks in a graph of tasks with some index. So instead of representing the entire DAG of computation, which could literally be, untold billions of tasks and pieces of data, what we want to do is just by parameterizing the task, we can describe the computation itself and execute the computation by essentially just looking at a wavefront of traversal of the graph at runtime. So we compose a graph that's not a DAG of these parameterized tasks, and as we're executing that graph at runtime, we're actually exploring the DAG. And so you can see sort of here some simple constructs mapped between these two. So here's a simple loop that is operating on a couple of vectors. And here is this sort of like parameterized graph equivalent to that, where we have some parameterized vectors coming into a parameterized computation. They're just chained together in the way that these dependencies do here, and then essentially producing this result. So clearly, we don't necessarily want to be writing this. We're going to have some DSLs, some supported data structures that enable us to essentially map from here to here efficiently, and that also gives us portability into different programming abstractions. And again, iteration just looks like recursion on the graph, and so that's just sort of like a reminder, this isn't a DAG. What gets executed at runtime will be a DAG. Don't need to look at that. So let's look at a specific example that's relevant to the multi-resolution computations. So we want to differentiate, and the key steps of differentiation is, if we want to say compute a central difference, right, we can think of this as sort of like an adaptive mesh, and here we're down at the finest scale of the mesh, and this is up at a coarser scale. And we want to differentiate a box. If we want to differentiate this box using a central difference rule, right, we need the value of the neighbor on both sides. We need the value of this box, the value of the left neighbor, and the value of the right neighbor. But this value doesn't exist, right? We have to compute it from the value up here at a coarser length scale. And so basically, you can sort of apply this process and turn it into this. And this leads to essentially two algorithms. One algorithm I sort of just described, which is, in order to compute this one, I say, aha, this doesn't exist. I have to look up for the parent, drag the value of the parent down here, compute the one that I want, and now I can compute and produce the result over here. But that doesn't lend itself to actually a very efficient implementation in any setting, and it certainly isn't amenable to a data flow or dependency style implementation. Essentially what we want to do in that setting is flow down the graph, right? And so what we want to do is essentially take that input function, which is a tree, and descend the tree, and when we encounter a box, that box is going to be interesting to the left and right neighbors thinking about the stencil that we want to apply. So we just send the box to those neighbors, where we just walk down the tree, send each box to every neighbor that might be interested in it, and just keep walking down the tree. And when we send the box to each neighbor, eventually each neighbor is going to receive all of the boxes it needs for computation, right? Some of those boxes may have been produced as we refine the tree going down, but eventually what we've done is turn this search and seek computation into something that is just streaming data down the tree, so intrinsically much more efficient. And just on these slides, just got some examples about what the code actually looks like. So relatively clean C++. We've still got a lot more work to do to basically essentially use template expression templates to basically make this stuff look like the actual formal math that it does, so we can avoid or eliminate all of this necessity of wrapping the computation up into templates, but a very concise modern C++ interface for it. So we have some demonstrations for this running on a variety of systems. These next few slides look at some of the preliminary results we had using this to map computation in a distributed memory setting onto processors with multiple GPUs. This was actually the first time this was done for a many-body chemistry code, so it was pretty exciting for the community to see that this was possible. I'm not going to go through this because in the end it's sort of like relatively mundane in terms of the performance obtained and everything. And I also want to get to the point where I can talk a little bit about MolSSI. So So NSF, as part of its SISI program, supports 3 levels of activities. Essentially solves single investigator grants, multi-investigator grants, and the very largest grants are these institutes. And so the Molecular Science Software Institute was one of 2 amongst the original batch funded. I think there's now at least 1 more. So it's a $20 million project that spans multiple institutions that is essentially out there to benefit the entire community in molecular science. So that includes not just chemistry, includes biophysics, large chunks of materials, and it spans not just basic science, but also touches on engineering and related activities. We are interested in moving forward in a very broad sense the capabilities and expertise of the community. It's a 5-year project. On success, we're anticipating being renewed for another 5 years. We've got some stories we're developing to sustain the key activities beyond that. One of the central things that we want to do is basically address this issue that in chemistry, in material science, in biophysics, still a lot of computation, a lot of innovation is happening in individual research groups, right? That's where many of the ideas are being developed. And many of those groups aren't connected with community projects or national lab projects that are at the frontier of computation. So there's this big divider between ideas being generated and those ideas being realized in the frontier computation. So one of the things we want to do is basically address that, and a key aspect of that is managing this overwhelming complexity of software. And this is just a small fraction of the large chemistry packages that are out there. These are, I think, just looking at, actually this is a molecular dynamics package there, but there's a whole load of packages missing. So this probably represents, well, where's NWChem? Somewhere on here. Oh, there it is, right? So NWChem itself is, I don't know, 3 to 5 million lines of code, depending on how you count. None of these codes are that much smaller than that. So on here, you probably got 40 plus million lines of code. And the entire community as a whole is going to have a lot more than that. So we have a massive effort in moving this software forward. And if we look at, say, the productivity enjoyed in other settings, like all of the software that you have on your phones and everything, these people are not writing software that looks like this, right? It's some OpenMP stylized code where we've annotated parallel loops and everything is very explicit, right? These people are developing code in a higher level setting. Now, they are solving different problems, right? And they do have larger budgets, which I certainly envy. But I don't believe they're solving easier problems than us, right? They've got their own complexities. And so, there are various aspects of this that we need to learn from in the way we develop our science, right? And a significant part of it is changing the dynamic in chemistry and material science to be more communal, right? So other disciplines like fusion, climate science, high energy physics, they sort of fairly early on, because they have a common understanding of what their science frontier is, right? They organize very early on around major community codes. That's still in process of happening in chemistry. There are large codes that are long-lived, used by many people, but we did an inventory of, say, density functional codes, and that's just a standard computational tool in chemistry and materials, and we found, without trying too hard, 650 density functional codes. Now, some diversity is crucial to the intellectual health of the community, but 650 of them, that's a whole separate story. And so we've got some perennial questions that actually we would appreciate your help with. So I think trying to get involvement from your community with not just MolSSI, but related activities would be really helpful, right? Everyone's always coming to us asking, you know, I'm starting a new project, right? What should I write it in, right? That question probably happens several times a day, right? And the answer that we really want to give people is don't, right? You should not be writing code as you understand it right now, right? I think the FFTW people and people generating high-performance kernels basically sort of put it very, very succinctly like this. As soon as you write do I equals 1 to 10, or whatever the equivalent is in C or C++, right, you've already locked yourself into a certain data representation, a certain language, a certain design of parallelism at the fine scale and the coarse scale. You've locked in so many things, you're at a dead end, right? You want to be expressing intent and having various tools to basically translate that intent into implementations in different settings. But clearly, the expertise to do this transcends individual groups in universities in the science setting, right? It's only by having larger community activities that we can do that. So for most people that aren't connected or don't have or sufficiently far afield, right? The right answer these days always seems to be OpenMP plus MPI. There are clearly settings where you can use optimized libraries and where you might have to resort to vendor-specific things. But this solution here, especially with the DOE systems, having had seismic shifts in their platform, have refocused DOE's attention on portable solutions for its own software stack. So they were always in the ECP activity, investing very heavily in OpenMP and other standards-based programming models, but at the same time, no one was using it. All of the code written, nearly all of the code, say, written for Summit was using CUDA, right? So they've got a massive re-engineering problem to move stuff onto the AMD box. I mean, fortunately, there's a almost one-to-one correspondence in some of the tools. But then if you look at the Intel box and its programming model, ultimately the same programming techniques, modulo the programming language, are necessary there. So there's a big push in the DOE setting to basically move back into this standards-based approach for a large chunk of the programming. And then, of course, coming from the university setting and looking at this larger community that we essentially want to re-engineer and reskill, there's always the question about what and how to teach. And I must say, we regularly hold these tutorials. Actually, this was one that we held just a couple of weeks ago at Stony Brook. It was a lot of fun. MPI was one of the things that we taught. And these days, MPI is actually one of the easiest things to teach, right? You can reduce it down to the usual 6 or 9 calls, and the students can grasp it very straightforwardly and see performance gains very readily. But I would say that it's harder to teach students how to reason about and analyze performance. And I must say that our ability to use, say, some of the sophisticated tools that we saw Tao being presented, it's constantly a challenge to get this stuff to actually work in practice. And I don't know how to navigate that. Maybe some of these discussions around containers and SPAC and things like that can address some of these issues. But ultimately, robust performance analysis tools that are ubiquitously available are still a challenge. And then another aspect of it is, again, focused on graduate education in science, in computational science, right? The students have to get a PhD in physics or chemistry or whatever they're learning. And so in most tutorial settings, we're only able to give them an introduction to computation, right? But some students need a deep dive, right? So we're actually partnering with the DOE labs to push some of our most interested and focused students into them to basically get some of that expertise. But I think other settings, working with this community, actually will be very helpful, and very helpful in a bi-directional sense, sort of like bringing some of the complexity of real-world applications closer to your groups. So I think I'm going to wrap up there, and thank you very much again for the invitation and all the great conversations. Thank you.
Okay, let's thank